Hello everyone, hope you are doing well. I am Akshay Parmar, Assistant Professor at LJIET Institute of Engineering and Technology in IT/ICT department. We have seen line coding techniques in our previous session, and it's one of type unipolar encoding, right? So in this session, we will cover the polar encoding. Right? Outline of today's session is the polar encoding, right? So in the polar technique, there are the four subtypes: NRZ, RZ, Manchester, and differential Manchester. In the polar line coding, there are mainly three subtypes: NRZ, RZ, and biphase. And in the biphase, there are two subtypes, right? So Manchester and the differential Manchester. That all the things we will see. That all the things we will cover brief in this video session, right? So polar line coding, right? So polar encoding use the two voltage level, positive and negative, to represent the binary, right? So polar encoding uses the two voltage levels, positive and negative. Polar encoding uses the two voltage level of the amplitude to represent the binary. Mainly the polar and line coding have the three major subtypes, right? NRZ, RZ, and the biphase. And in the biphase, there are two subparts there: Manchester and the differential Manchester, right? So let's see one by one them. NRZ, non-return to zero. In the NRZ encoding, the level of the signal is always either a positive or a negative, right? The polar NRZ have the two subtypes, NRZ-L and NRZ-I. Here L is represent the level signaling and the I represent the signal get inverted, right? So let's see the NRZ-L in brief, how it's working, right? So NRZ-L is a in the NRZ-L, the level of the signal depends on the type of the bit it represents. The positive voltage usually means a bit 0. A positive voltage usually means a bit 0, and a negative voltage means a bit 1, or it can be a vice versa, right? So thus the level of the signal is depend upon the state of the bit. Let's see by the example, right? So here we have the bit sequence 0 1 0 0 1 1 0. So positive voltage usually represent the bit 0 and the negative voltage will represent the 1, right? So it may be vice versa, right? The positive voltage will introduce a bit 1 and negative voltage will introduce a bit 0, right? So in this session we have taken a positive voltage to represent the bit 0 and the negative voltage to represent the 1. To represent this bit sequence, the 0 bit will be represented by the positive voltage, right? After that, the second bit is there, that is the 1. The 1 is represented by the minus. The 1 is represented by the negative voltage, right? So 1 is represented by the negative voltage. After that, there is a 0 voltage. So 0 voltage will be represented by the positive voltage, right? So it will be represented by the positive voltage. Another, there is a 0 voltage, so there is a no change because it is already at the positive voltage. It will continue its path, right? After there is a 1 bit, so that will be represented by the negative voltage, so it will go through the negative voltage. After that, another 1 is there, and after that another 1 is there, so the negative voltage is represented that one, right? After that, the last bit is 0, that will be represented by the positive voltage, right? So that's how the NRZ is working. This is how the NRZ-L encoding is working, right? So let's see the NRZ-I, the inverted bit, right? So NRZ-I, in the NRZ-I, an inversion of the voltage level represent a 1 bit, right? So in the NRZ-I, the signal is inverted if 1 is encountered. A 0 bit is represented by the no change, right? We have started with the positive voltage to represent the 0 bit. Whenever the 1 bit is encountered, we will invert the voltage of that current state, right? So we have started with the positive voltage to represent the 0. After that, the bit 1 is there, so we will invert that voltage, right? After the 0 bit, the 1 bit is there, so to represent that bit, we have to invert that state of that bit, right? So we have already the positive voltage to represent the 0, so we will invert that and represent the 1, right? So after that, there is a 2 0. After that, there are the 2 zeros there, right? So 0 bit is represented by the no change, right? So after the 1, there is a 2 0 bits, so there is a no change, so it will be continuous in that path only. After that, the 1 is there, So one is represented by the inversion of the previous bit, so it will go to the positive voltage, right? After that, another one is there. After that, the another one bit is there, so it will be inversion of the, to represent that bit we have to invert the previous bit, right? So it is, one is represented by the positive voltage, after the another one is represented by the inversion of that previous bit, right? So we will represent the second one by the negative voltage, right? After the third one is there, so it will be represented by the inversion of the previous bit representation, right? So that third bit will be represented by the positive voltage, right? So this is how you will you will invert the previous bit to represent the one. Whenever the one is encountered, the its previous bit is inverted to represent that bit, right? After that, the zero is that, and zero is represented by the no change, right? So it will be continuing like that, right? So this is how you can represent the bit sequence in the NRZI. This is about the NRZ, right? So let's see the RZ, the return to zero line coding, right? So in the RZ, the signal changes not between the bits during, but during the each bit interval, right? So problem with the NRZ is that the receiver cannot conclude when the bit is ended and when the next bit is started. In case of sender and receiver, clock is not synchronized, right? So to overcome this problem, the RZ technique is there. The here the one bit is represented by the positive to the zero, and the bit zero is represented by the negative voltage to the zero, right? So here the bit sequence is same, 0 1 0 0 triple 1 0, right? So initially the zero bit is there. To represent the zero bit, it will be represented by the negative voltage to the zero, right? So this is how you will represent the z bit zero. The zero is that, so to represent the zero, negative voltage to the zero voltage, right? This is how you will represent the bit zero. After that, the one bit is there. So to represent the bit one, we represent it by the positive voltage to the zero, right? So to represent the bit one, we will move forward about to positive voltage, and after that again reach to the level zero, right? After that, zero is there. So to represent the bit zero, we will go to the negative voltage, and again we will reach to the level zero. After that, again zero is there. To represent the bit zero, we will follow that method, the negative voltage to the zero, right? So again we will reach to the negative voltage and reach again to the zero voltage. After that, the one voltage is there. So to represent the bit one, positive voltage to the zero voltage, right? This is how we will represent the one. After that, another one is there. So we will follow that rule only, right? So to represent the one, we will reach to the positive voltage, and in the second half we will reach to the zero, right? So this is how we will represent the bit sequence in the polar RZ, the return to zero. This technique is called the return to zero because after the each bit we will returning to the zero. We are returning to the zeros amplitude, right? So as you can see that even if you are at the zeros bit or the ones bit, you have to return to the zero level, right? If you are at the bit zero, you have to reach to the zero level from the negative voltage, and if you are at the representing the bit 1, you have to reach to the level 0 from the positive voltage, right? So that's how it is called the RZ, return to zero technique, right? So after that, the third type, the biphase. In the biphase technique, there are the two subtypes, Manchester and differential Manchester. Let's see the Manchester technique in brief. In the Manchester encoding, the transition at the middle of the bit is used for both the synchronization and the bit representation. By using a single transition for a dual purpose, the Manchester encoding achieves the same level of the synchronization as the return to zero, but with only the two level of the amplitude, right? So this is all about the Manchester technique. Let's see its bit representation. In the Manchester encoding, the positive to the negative voltage transition is represent the binary 1, and the positive to the negative transition represent the bit 0, right? So here we will represent the bit sequence 0 1 0 0 1 1 0. So in the Manchester encoding technique, right? So to represent the bit 0, we will follow the positive amplitude to the negative amplitude in the transition, right? So to represent the bit 0, we will follow the positive to the negative, the positive to the negative. After that, the 1 is there. To represent that bit 1, we will follow the negative voltage to the positive voltage, right? So we will follow the negative voltage to the positive voltage, right? After that, we will have the bit 0. To represent the bit 0, we will follow the bit positive voltage to the negative voltage, right? So we will follow the positive voltage to the negative voltage. After that, again the bit is 0. To represent that bit 0, we will follow the same formula. Positive voltage to the negative voltage. We will follow the positive voltage in the first half of the bit, and in the second half we will reach to the negative voltage, right? So that's how we will represent the bit 0. After that, bit 1 is there, so it will be represented by the negative voltage to the positive voltage transition, right? So we will represent the bit 1 by the negative voltage to the positive voltage transition, right? So that's how we will represent the bit 0 and bit 1, and that's how we will represent the bit sequence in the Manchester encoding technique. The another type of the biphase is the differential Manchester, right? So let's see the what is the different in the differential Manchester. In the differential Manchester encoding, the transition at the middle of the bit is used only for the synchronization, where in the Manchester technique it is used for the both synchronization and the bit representation. But in the differential Manchester technique, the transition at the middle of the bit is used only for the synchronization. The bit representation is shown by inversion or the non-inversion at the beginning of the bit. It requires a two signal channel. It requires two signal changes to represent the binary 0, but only one to represent the binary 1. Let's see how it's working, right? So let's have an example. The same bit sequence 0 1 0 0 1 1 0. A transition means binary 0 and no transition means binary 1, right? So here we will represent the bit 0 by the negative voltage to the positive voltage, right? After that, to represent the bit 1, there is a no changes. Let's see how the differential Manchester is working, right? To represent the bit 0, we will follow from the negative voltage to the positive voltage in this initial level, right? After that, the bit 1 is there, right? So to represent the bit 1, we will invert our previous bit, right? So to represent the bit 1, we will follow from the positive voltage to the negative voltage, right? So that's how we will represent the first bit, first occurrence of the bit 1. After that, the bit 0 is there, so there is a no change in the transition. So we will follow the previous method, the positive voltage to the negative voltage, right? So we will follow the positive voltage to the negative voltage to represent the bit 0, right? After that, again the bit 0 is there, so there is a no changes in the transition. It will represent the positive voltage to the negative voltage. After that, the bit 1 is there, right? So to represent the bit 1, we will invert its sequence, right? So here the bit 0, the previous bit of the bit 1 is 0, and it will be represented by the positive voltage to the negative voltage transition. So to represent the bit 1, we will follow the negative voltage to the positive voltage to represent that bit 1, right? So that's how we will represent the second occurrence of the bit 1. After that, the bit 1 is again bit 1. So to represent that bit 1, we will represent it by the inversion of the transition, right? So again the 1 is there. So to represent that bit 1, we will inverse the transition of the previous bit, right? The previous bit is represented by the negative voltage to the positive voltage. So to represent that bit, we will follow the positive voltage to the negative voltage, right? So that's how we will represent the second occurrence of the bit 1, right? After that, the third occurrence of the bit 1 is there. So we will follow the same rule, the inversion of the previous transition, right? So previously, the previous bit is represented by the positive voltage to the negative voltage transition, right? So we will follow the negative voltage to the positive voltage transition to represent that bit, right? So that's how we will follow that rule and represent that last one bit by the negative voltage inversion to negative voltage to positive voltage transition. After that, the last bit is 0. So to represent the bit 0, there is a no transition changes. So we will follow the transition method of the previous bit, right? So we have followed the negative voltage to the positive voltage. So we will follow that rule and we will represent the last 0 bit by the negative voltage to the positive voltage transition, right? So that's how we will represent the bit sequence in the differential Manchester encoding technique, right? So in this session we have seen the polar techniques or the polar line coding techniques. In that we have briefly seen the NRZ, RZ and the biphase techniques, right? So in the NRZ we have seen it's two types, NRZL and NRZL, NRZL and NRZI, and how it's represent the bit sequence. After that we have seen the RZ technique in brief, and in the biphase technique we have seen its two subtypes, Manchester and the differential Manchester in the brief, right? So this is all about today's video session. Thank you for the watching.